Hi there! This week is all about hypothesis testing. In this video we will see what this actually means and we will perform such a test. Let's consider the following example. Nowadays there are several techniques to get rid of kidney stones. The open surgery technique has long been the go-to technique, but new treatments have become available. One of them is using laser pulses. When such a new technique is being developed, one of the sensible questions is whether this technique is more successful at its job. Does it have a higher probability of success than the usual treatment? Well, let's investigate. At the beginning of this century, the open surgery technique was well known and it had a probability of success of 78%. In this setting, success is defined as the full removal of all kidney stones after the treatment. What proponents of the new technique would like to prove is that their technique is more successful. For this, a hypothesis test is well suited. We introduce two hypotheses, each representing one of the two beliefs. The first one is called the null hypothesis, H0. It states that the new technique has the same probability of success as the old one. You can interpret this as being the default situation, where there is no difference between the two techniques. Hence, our null hypothesis becomes theta equals 0.78, where we define the unknown theta to be the probability of success using the new technique. We would like to show that theta is greater than this value. This will become our alternative hypothesis, H1. Note that these two hypotheses play different roles. The alternative one is the one you seek evidence for. If you find enough evidence, you will reject the default null hypothesis in favor of the alternative one. If you do not find enough evidence, you will not reject the null hypothesis. We will base our final judgment on the data. Well, let's use the data collected by Hussein and collaborators in 2011. They found that out of 236 patients that were treated with the laser technique, 215 reported full removal of kidney stones. Let's denote this observed proportion by theta hat. This notation makes sense, with last week's terminology in mind. This observed proportion is an estimate for the unknown probability of success, theta. Obviously, this is very likely not the true value for theta. Had they taken a different sample, the observed proportion would probably have been different. It is, however, clear that theta hat, 91.1%, is quite a bit larger than 78%. So, do we reject the null hypothesis? Well, not so quick. After all, we may just have been lucky. Well, the way we now proceed in our hypothesis test is crucial, so this is a really important step. We will assume that the null hypothesis is true, and then assess how extreme our observation is. We will do that in a moment, but hopefully you already see where this is leading. If it turns out that our observation is very extreme, it will lead us to doubt the assumed null hypothesis. If our observation is not very extreme, then we have no real reason to doubt the null hypothesis. We don't have enough evidence to reject the null hypothesis. By the way, notice the wording here. We say we do not reject the null hypothesis, rather than we accept the null hypothesis. In this case, we just don't have enough evidence against it. Let's denote by the random variable t the number of successful treatments in our sample of 236. T will be the quantity that we base our final decision on. We call it the test statistic. In our example, t takes the value 215, which we denote by little t. Now, we know quite a lot about this random variable capital T. We know its distribution. Do you? You can pause the video if you want to think about this. Well, Since t counts the number of successes in a fixed number of identical independent experiments, t has a binomial distribution. Here we made the quite sensible assumptions that each patient has the same probability of their treatment being successful, and that the outcomes for the patients are independent. The parameters of this binomial distribution are n equals 236, the number of experiments, and the probability of success is exactly what we call theta. Moreover, under the assumption of the null hypothesis, theta equals 0.78, we find that t has a binomial distribution with parameters 236 and 0.78. Here you see that the probability mass function for t under this assumption of h0. As we can check using R, the probability that t equals 215 is equal to 5.2 times 10 to the power minus 8. This is a very small probability. However, we need to be a bit careful here. Even the most likely observation, t equals 184, only has a probability of 0.06, so not very high. And you can easily imagine that with larger n, the probability of getting exactly a certain number will be very small. Not to mention the continuous case, where the probability to get a specific outcome is always 0. So, rather than looking at the probability that t equals 215, we will look at the probability that t is at least 215. The argument for this is that an even larger observation, like 220, would be even more convincing. It would be even stronger evidence for rejecting h0. So, in this way, we are checking how extreme our observation is by considering the probability of getting our observation, or an even more extreme one. In our case, the probability that t is at least 215 is equal to 7.8 times 10 to the power minus 8. In hypothesis testing, this probability is called the p-value. By the way, this is why we call the unknown proportion theta rather than p, to avoid confusion. Oh, and did you notice the R command? This p by num expression gives you the probability of getting at most 214 successes. The complement of this is the probability of getting at least 215 successes, which is what we wanted. The value is actually so small that we had to tell R to take more digits into account, otherwise it would just tell us that this is 0. In general, the p-value is defined in this quite lengthy way. It is the probability, under the assumption of the null hypothesis, to obtain the observed value for the test statistic, or a value that is even more extreme, even more convincing of the alternative hypothesis. It is a very important concept though. When you encounter a statistical test in a paper, the corresponding p-value will always be reported. Here we zoom in on the right tail of the probability mass function. Notice the very small values on the vertical axis. Well, to me this p-value seems like a very low probability. Think about it. If the null hypothesis is true, we will only see an observation greater than or equal to ours in 78 out of a billion cases. This will lead us to doubt the null hypothesis, and we will reject it in favor of the alternative one. However, are we certain that we made the right decision? No. It might be that p is actually equal to 0.78, but that we just made a very extreme observation. If that is the case, we have made a type 1 error. This term obviously makes you think that there is also a type 2 error. Well, there is, and you will hear more about those errors and the probability of making one in the upcoming videos. Finally, I think you'll agree that 78 in a billion is indeed very small. But what would you decide had it been 0.001? Or 0.01 or 0.1? Well, sometimes we will answer this by putting a threshold value at the start of our hypothesis test. More on that as well in the next video. By the way, we can do the same analysis using R. This can be done by the following command called binom.test. You need to give the number of successes in the dataset, 215 in our case. The second argument is the total number of trials. In our case, this n was equal to 236. And the third argument is the probability of success according to the null hypothesis. In this example, this was the value 0.78, probability of success before the introduction of the new technique. Next up is the alternative hypothesis, which also appears in the output. And the final argument is an optional confidence level, the complement of the significance level. It is a concept that we will encounter later this week and next week as well. In the output, you recognize the observed proportion, 91.1%, and the p-value that we found as well. The confidence intervals you see here are next week's topic, so please be patient for more information on those. Well, there you have it. This was our first hypothesis test. It was a test on a proportion, since the unknown value we tested for was the proportion theta of successful treatments. But we can test hypotheses on all kinds of parameters. You will encounter more of these tests during this week, both in the videos and in the exercises. See you then!